Hello everyone, my name is Jeffrey Simpson. I'm the chair for this session, which is all about first stars. So our first talk is from Gary Costa at ANU giving the overview talk. So over to you, Gary.
Okay, thanks, Jeffrey. For those of you who don't know me, I'm Gary Costa. I'm an emeritus professor at the ANU, and I'm the First Stars project lead. The first thing I want to say a little bit about is something that I don't think has been mentioned too much so far, and that's welcoming the new nodes. We originally were going to have a meeting back in July. We were going to have a nice slap-up dinner where we would actually welcome the new nodes. But I'd like to just point out that the new nodes in particular are bringing quite a lot of new expertise into the First Stars project. For example, at Monash, we have a whole group of people whose names I've listed there, and I'm sorry if I've missed anybody who feels as if their name should be there, but they bring a whole lot of expertise in stellar evolution, and in particular the nuclear synthesis of elements from both AGB stars and supernovae. And this is the sort of vital material that we need for interpreting observations of the first stars and the chemical elements, and particular chemical dynamical models of the Milky Way. And then there's UNSW and Macquarie, where people like Sarah and Jeffrey and Dan Zucker are bringing expertise in, particularly as regards stellar streams in the galaxy's halo. Understanding stellar streams is vital if we want to understand the buildup of the galactic halo, and they also provide opportunities to constrain the mass of the Milky Way and of the OMC. And then, of course, from the University of Hertfordshire, we have Chiaki, who, of course, is a world leader in producing chemical dynamical models of the galaxy. And we've seen this once today already, but I thought I should show it again. It is really an impressive figure which summarizes an enormous amount of astronomy, where you can basically pick any element you like, and you can see what the models tell you about how that element builds up as a function of time. For example, you look at iron, you see you have a major contribution from type 1a supernovae, but also from, more importantly, from core collapse supernovae. The S process elements, or the more better described as the neutron capture elements, have a major contribution from AGB stars. Other elements, come from neutron star mergers, for example. So this is an important description of how the galaxy, the elements of the chemical elements of the galaxy build up as a function of time. So I'm just going to talk about some science highlights. In the subsequent talks of this, you will hear some other exciting science. Let's start off by pointing to a theoretical paper by PhD student Piyush Sharda and his supervisors about how magnetic fields can affect the primordial mass distribution of stars. And what they conclude is that the development of dynamically important magnetic fields during the formation of the first stars is likely inevitable, and those magnetic fields have a significant impact on the primordial IMF. And in fact, they basically suppress the formation of low mass stars. And you can see that on the figure here. The green histograms are those calculated in the presence of a strong magnetic field. And you can see that relative to the ones with weak or no magnetic fields, there's a much higher fraction or much lower fraction of low mass stars. In fact, you're actually not seeing very many stars below 1 solar mass at all. And that's shown here also in the cumulative distribution, where basically the low mass stars are not formed. And of course, we have no evidence of there being any primordial stars that we see in the present day. So no low mass stars have survived to the present day. Another interesting result has to do with globular clusters. The globular clusters that we have in our own galaxy now seem to have a metallicity floor of around -2.5. There are no present day clusters that have metallicities below this value. And so a question arises as to whether this is a consequence of globular cluster formation processes, in the sense that they only form at abundances above this limit, or is it some other effect that we don't see? Now, some recent work on the Phoenix stellar stream provides us some new insight into this question. A paper published last year by a University of Sydney PhD student in Nature and 2 subsequent follow-up papers have actually told us a lot about this question. Now, what is the Phoenix stellar stream? It's a thin overdensity of stars that spans about 8 degrees in the southern sky. Stellar streams are the remnants of either tidally disrupted globular clusters or tidally disrupted dwarf galaxies. And when you look at them, you can see that in some cases, they have distinct progenitors. For example, the globular cluster PAL5 long been known to have extensive tidal tails that extend either side of the cluster. Or from the Sagittarius dwarf galaxy, we know that the disrupted galaxy is being disrupted, and in fact, the tidal tail of this disrupting galaxy is spread over a large amount of the southern sky. But for a system like Phoenix, there actually is no obvious progenitor. We don't really know what is being disrupted. Now, there's been a large international collaboration that's been studying stellar streams with the AET. It's called S5 for Southern Stellar Stream Spectroscopic Survey, and it contains a number of Astro3D affiliated astronomers from the ANU, from Sydney, UNSW, Macquarie, and Monash. We use 2DF plus A omega to spectroscopically identify stream members through velocities and metallicities. And we actually observed 8 fields in the Phoenix stream and found 25 probable members. And of those, enough of the red giants had good signal to noise so we could measure metallicities. And so in the black dots here represent the metallicities determined for the stars in the Phoenix system. And the Warnadel paper concluded that you can see here that there's no evidence for an intrinsic spread in iron abundance in the observed sample. And so that very strongly suggests that the progenitor was a globular cluster and not an ultra-faint dwarf galaxy. Globular clusters in general don't have iron abundance spreads, whereas ultra-faint dwarf galaxies generally do. But you can see the mean metallicity of these stars is actually minus 2.7, well below the abundances of galactic globular clusters. And in fact, the blue histogram here is the histogram of metallicities of all the galactic globular clusters. You see the peak at around minus 1.5 for the halo clusters, and then the peak around minus 0.5 for the disk and bulge clusters, but none of them are down here. So the Warnadel paper concluded that globular clusters with metallicities below the current floor probably did exist, but were destroyed during the galactic evolution. Now, we've had high dispersion follow-up of 8 red giants with Magellan, and they confirmed the AET results, that the metal abundance really is minus 2.7, and the intrinsic dispersion in iron abundance is essentially 0. Now, the question we can ask from these high-resolution spectra is, do we see the same kind of internal light element abundance ratios that we see in regular globular clusters? Basically, anti-correlations between carbon and nitrogen, sodium and oxygen, and aluminium and magnesium. And now, for the Phoenix stars, we can't actually measure oxygen abundances because the signal to noise in the spectra is not very hard. We can only get loose upper limits on the abundances. The grey points here are the regular globular clusters in the galaxy. And we see as sodium goes up, as oxygen goes down. The Phoenix stars have actually seemed to show the same thing, that there is a distinct spread in sodium that covers basically the same range as we see in the regular globular clusters. And the same if we look at aluminium. We don't actually see any change in the magnesium abundances in the stars, but that's not too surprising because magnesium, you don't need to change the magnesium abundance very much to get a big change in aluminium because aluminium is a much less abundant element than magnesium. And so we do see here, though, again, the dark grey pots are regular globular cluster red giants, and we do see the same kind of correlation between sodium and aluminium. So the sodium aluminium results and the lack of the dispersion in Fe/H really do suggest that the progenitor of Phoenix was a globular cluster, despite having a metallicity lower than any one we have at the moment. So that really does imply that globular clusters less than minus 2.5 likely did form at early times, but they've been subsequently disrupted by tidal interactions. The S5 group has actually also studied another stellar stream that has a globular cluster progenitor from a lack of Fe over H variation, and it also has quite a low abundance of -2.4. The other point about the finished results shows that, in fact, the unknown, whatever the process is that drives the globular cluster light element abundance variations, it can still operate at low metallicities.
That's 2 minutes, Gary.
Fine. So the only other paper I wish to talk about is a very substantial paper for which David Yong is the first author of. It shows basically detailed chemical abundances for over 150 metalpoor stars. Those metalpoor stars were originally selected from sky mapper photometry and have been followed up with Magellan and Mike, basically. 90 of the stars have abundances below -3, 15 have below -3.5, making it one of the most largest sets of consistently analyzed metalpoor stars. Now, there's a number of results, and you'll hear some about them subsequently, but one that I do want to mention is that we've discovered what is the lowest iron abundance R-processed element enhanced star. That paper was the subject of a recent Nature paper and an Astro 3D press release, which shows that, in fact, we can synthesize the R-processed elements from a magnetorotational hypernova rather than from neutron-star mergers. And that paper really does give us an extensive view of the early chemical evolution of the Milky Way. And that shown here, where the underlying red data are the stars that we have detailed abundances for. You're basically seeing element to iron ratios against iron abundance. And note that we started around -2, whereas every other plot you've seen so far today, -2 is never on the axis. The filled circles are the means in 0.5 dex bins, and the blue dashed lines are predictions from Chiaki's models. And what you can see here is if you look at, for example, at magnesium or calcium or titanium as alpha elements, there's really very little scatter as a function of iron abundance. These elements, the nucleosynthetic processes are producing consistent results. Same is true if you look at the iron peak elements like chromium or nickel. They show very little scatter as iron changes. On the other hand, if you look at things like carbon or nitrogen or the neutron capture elements, strontium and barium, you see enormous scatter, indicating that there really is large variations in the nucleosynthetic processes that produces these elements. The other point that I want to make from David's paper concerns the metallistic distribution function. In the panels here on the first side, you see the data from the SkyMapper sample, and on this one, an earlier study from David had done with John Norris. Now, these are completely independent samples, but in both cases, you see a very steep decline in the metallistic distribution function as metallicity decreases. And the red points here are, in fact, carbon-rich stars. And then in this part over here, you actually see the slope that we get a slope of 1.5 for the number of stars changing, or logarithm of the number of stars changing with metallicity. And that's actually in good agreement between with a photometric study from the Pristine group. And there are two important results on that. First, as I said, that the metallicity slope is -1.5 and not -1, as sort of simple models of chemical evolution predict. And that just shows you how rare these stars are. You know, if you're 30 stars at -3, to have one at -4. The other point is there's really an abrupt change of slope or cut in the metallistic distribution function, somewhere around -3.5 to -4. The stars below that cutoff extremely rare. And in fact, basically all of the stars below with iron abundances below -4 are actually all very metal rich. So if you consider their total metallicity, not just their iron abundance, their overall metallicity, in fact, is relatively high. And so both of these observational results need to be taken into account when you want to understand how to form so-called second generation stars, those low mass stars that were the first to form after the first generation of primordial stars. So just to end then, I think the First Stars project is a very active group. We've got collaborations across all the nodes, and I expect it to continue to be productive in the future. We're about to hear some interesting scientific presentations. So look stay tuned for those. And then thanks to everyone involved in the First Stars Research Group for making it such an active group. Thank you.
Thank you, Gary. We have time for a short question if anyone has a question. Remember, you can raise your hand or type it into the Slack. Piyush has raised his hand.
Thanks, Gary. I was just wondering, so the Fe over H less than -4 stars that are very carbon rich, is this carbon richness based on NLT or LTE modeling?
It's based on non-LTE modeling. There's a paper by John Norris and David Yong, I guess, a couple of years ago, where they looked at the NLTE corrections to the LTE carbon abundances. But yes, the high carbon abundances are indisputable.
Okay, thank you.
Okay, so we should move on to the next talk. So thank you, Gary, again.